Okay, good evening, everybody. Welcome to the second of the beginner's guides. This one is by popular demand, the astrophotography talk. I'm quite aware that people in the meeting will have various degrees of expertise in this subject, and I'm not an expert on this. I can tell you about basically the things that I've done and the tricks that I've picked up. And if you want to kind of like elaborate on what I've talked about at the end of the meeting, we can do that. If there's things you think I haven't covered that we might want to talk about, we can do that as well. Anything that you think of, you can either wait until the end and there'll be time for discussion, or you can put it into the chat and either me or Kathy will flag it up at some point. Okay. Right, so let's get started. So this is kind of what I want to cover, and I've got to constantly remind myself that this is a beginner's guide, and therefore I'm not going to go into much of this in a lot of detail. There's a lot of pictures to show you, and in some cases I'm just going to show you the picture and then kind of like tell you the settings that I used to take the picture. I will go through some of the general principles that apply to taking pictures with a DSLR or a CCD camera. So things like taking flats and bias frames, I'll mention those and what they do. We're looking for signal to noise ratios being good usually when we take pictures, so I'll explain a little bit about that. I want to talk about how you can use just a DSLR to take pictures of the sky. You can do that on a fixed tripod without any tracking. If you want to take pictures of galaxies, star clusters, nebulas, you might want to do that with a telescope, in which case you'll need a mount that can track. So again, I'll talk a little bit about that. Whenever you're taking images with the DSLR, you really need to be using the raw images rather than the JPEGs. Again, it's to do with kind of the quality of them, and I'll mention a little bit about that if you didn't already know that. There are a lot of CCD and CMOS cameras on the market. Again, I got one of these fairly recently, and these are great for doing broadband and narrowband imaging, taking pictures of, again, galaxies and so on. You can also obtain quite fantastic pictures of the moon and planets using these cameras as well. You use them in a different way. Rather than long exposures, you take thousands of pictures at short exposure and select the best of them for further processing. This is called lucky imaging, and I'll tell you how to do that as well. I will keep track of the software that I'm using to do all this stuff, so I've got a bit of a list at the end. And after that, a Q&A if you've got anything you want to talk about there. Okay. Right, so back to basics. Astrophotography is about acquiring images of astronomical objects. Why you would want to do this is because cameras can pick up more light than your eye can see. Cameras collect light over a period of time. Your eye has a very narrow pupil which allows light into it, so it's not a big aperture, and therefore you're always going to be able to collect more light with a camera if you let it collect light for a long period of time as well. There are different ways you can take pictures of the sky and the different objects, and I've mentioned those. The particular choice of equipment and configuration really depends on what you're trying to take a picture of, and it should be said that I'm focusing on the for fun side. Okay, so astrophotography has its place for serious science. I'm not really going to go into that tonight, so this is more of the arty for fun side of things this evening. It's not to say that you can't, for example, discover new storms in the atmosphere of Jupiter with astrophotography, because you can do that, and that's pretty serious science. But mostly we're processing our pictures for fun, the sheer joy of it. Now, when you take pictures of things in the night sky, we talk about the object that you're trying to take a picture of, okay? And the light from that object travels through the universe, sometimes for seconds, sometimes for millions of years, and it goes through the aperture of your telescope. It gets focused onto a camera sensor, and then you read the sensor out and you get data, and the data might be rubbish. It might look really terrible, and you might be disappointed with how it looks when it comes out of the camera. Okay, but this is basically the image formation model. So we're trying to photograph these amazing objects, but the imperfection is our telescope and camera, and whatever we record, we want to try and improve on that and get a good picture out of it. Now, in general, when we try to take images either through a DSLR or a CCD camera, they're not perfectly captured. In fact, there are components mixed together. The good bit is the object, which we will refer to as the signal, okay? So that might be a galaxy or a nebula or a star. But due to the quantum nature of light, there is noise associated with the signal. Okay, this is because when you've got a light source, the light is composed of photons, and there's a random variation just because of the nature of light, which means that you don't get a constant number of photons every second. And even from the background sky, you get a varying number of photons of light, and these come mixed together and they impact your camera sensor. And therefore, when you record an image, you've got a mixture of signal and noise. To get a good picture, we define this thing called the signal to noise ratio, okay? And we want that to be a big number, okay? So signal to noise ratio, we want the signal to be far more important than the noise. To achieve that situation, we usually have to use calibration images, okay? And what we can also do to boost the signal as well is to take lots and lots of images and combine them. We stack them, we combine them, integrate them. And that's something which a lot of software can do without much input from you. You just have to give it a list of images, and the software will generally do this for you. You just have to provide the images. So stacking images works by kind of averaging together each pixel. So if you look at the picture on the right of the screen, that's meant to represent kind of the pixels in a series of images that you've taken. And the arrow is pointing at one of the pixels. So for example, in the first picture, maybe the intensity is like 100 out of 255, okay? So it's like a gray pixel. In the next one, because of the random variation in light, it's 102. And the next one, it's 98. So in successive pictures, it does that. And then suddenly, something hits it. Maybe it's like a cosmic ray or a hot pixel, and it's got 900 there. That's a bright white pixel. And then it's back to 101, okay? Now, what stacking images does is it basically will remove the effect of that 900, and it will come up with an average value of all of the others together. By doing this, what you do is you smooth out the effect of the random noise in your images. It kind of evens it out so that there's no kind of extreme values. And the more you do, the less noise you're going to get in your final image, the higher the signal to noise ratio will be. The signal to noise ratio mathematically is proportional to the number of photons that you collect. And usually that means if you're taking pictures, it's proportional to the square root of the number of pictures that you take. So the more pictures you take, the higher the signal to noise ratio will be, and it follows a kind of fairly rigorous mathematical pattern. Okay, so if the only thing you take from this is more images means high signal to noise ratio, that's what you should take from this. This is kind of how it works in practice. You take a lot of pictures of your target, and they're not very good. They're a little bit grainy. They don't look very good. The other thing I guess I should say about this presentation is, because you're watching over an internet connection, some of the effects might be lost because of the fact that we're on Zoom and you're not in the room, we're looking on a projector, okay? So this is a noisy image of a galaxy, and there are several of them, and they look not great, okay? So you average them together, you combine them, and you get one super image of the galaxy. That's the idea of what you do. So by combining these images, the graininess of the background is smoothed out, and you get a nicer picture, a higher signal to noise ratio. Now, as well as that, there are other sources of noise, not just due to the random nature of photons impacting your sensor. Your camera itself has a source of noise. It's called thermal noise. So the warmer the camera is, the more random noise there is on the sensor. So you take dark frames, and this is just about covering either the telescope aperture, and then taking the same picture as you just took for your object, but with the telescope covered. And ideally you take the same number of exposures. So the same, you take them, maybe you do like an imaging session where you take all your pictures of M31, maybe 2 hours of them, and then you're done. You cover the telescope up, maybe you put the telescope away, but you leave it overnight for the rest of the night to take your dark frames, and you get like 2 hours of darks. And you stack them together and you get an average picture of the noise within your camera. This is a picture of what the dark frame from my old Nikon D80 looked like. And there's a lot of kind of noise in there. I've bumped the contrast up to really show what the camera is, but this is like the telescope is covered and it's taking a picture of nothing. But instead of getting a picture of nothing, I've got a picture of the noise within the camera, the kind of the random signals and the amp glow. So I need that because that was in my picture of the galaxy when I took it, and this is just a picture of it, so I should be able to correct for that. The other thing is a flat frame. This corrects for kind of vignetting around the edges or the non-uniform illumination of your sensor. If you've got anything like dust particles on your camera sensor, this will take a picture of them. So you point your telescope at either the sky during the daytime or twilight, and you take a picture of a nice flat background. Mia's got a light box for her art kind of work, and I use that. I hold that in front of the telescope and take a picture of that, and that works brilliantly. This is a picture of a flat frame, and you might be able to make out there's kind of like a grey splodge on here. It's a little dust particle slightly out of focus in front of the sensor. It's dark in the corners, and again, in my picture of a galaxy, this is an effect which affects the background, and we can now correct for it. The bias frame is where you take a picture of the shortest possible exposure. So on my Nikon, it was like 1/4000th of a second. And it's a picture of the differences between pixels in the sensor before you expose it to light. And again, that's what it looked like for my Nikon D80 when I used to have it. And it's just kind of random noise. But again, that is in my picture of a galaxy as well. So this is kind of what you do when you do calibration. Oh man, it's always something. So there's the picture I took, and I've exaggerated the effects here, but you've got amp glow, it's noisy, it's horrible, and you're subtracting the dark, the flat, and the bias to leave your calibrated image for further processing. So you could then apply that to each of your images and then stack them together to get one final amazing image. So you do this no matter which kind of camera you've got, okay? So if you've got a DSLR, you could do this. If you've got a CCD or a CMOS camera, you could do this as well. This is something which is shared by all of the other techniques that I'm going to show you this evening. Right, okay. I've really skipped over a lot of the detail there, okay? Now, the simplest kind of photography that you could do is just with a camera on a tripod, I guess. You can even do some of these things with good smartphones now. So again, some of the pictures you're going to see, I've seen them online with people doing them with smartphones. So, you know, this is pretty basic stuff, but a tripod is necessary to avoid vibration or shaking during the exposure. There's no way you could keep still enough for like 5 or 10 seconds without, you know, just holding it in your hand. A remote control or a timer would be a good idea, so you can set lots of exposures and then you can just go and have a cup of tea or do something else. And here's the first example picture. Took it last winter, and it's Orion with some trees in the foreground, and it was a cloudy night because we're in Northumberland, obviously. but this was on a Nikon D90. It was an 18mm lens, ISO 400, f3.5. That's 15 seconds. It was the moon was out as well, which is why the sky didn't look completely dark. That captured just about all of the stars you could see with the naked eye. 15 seconds with those settings is enough to get all the stars you can see in the sky with your eye. I chose a low ISO, which is the sensitivity of the camera, because with the lower sensitivity, although you have to expose for longer, it picks the colors up a lot better on the Nikon. So I chose that rather than something like ISO 1600, say. The aurora can be captured when it's visible. Again, this was taken from Acklington, just around the corner. Almost the same, well, it is the same camera, same lens. ISO is a bit higher. That's a 30-second exposure. I think the Andromeda Galaxy is in there as well. I can just see that there. It's picked out the Andromeda Galaxy as a bit of a smudge there. Cameras always make the aurora look more dramatic than they are with the eye. So this is where things get a little bit misleading when you post things like this on Facebook or Twitter and you think, wow, look at that, look what I missed, I didn't see that. And really it was just the barest discernible glow on the horizon when I took this picture. But again, camera on a fixed tripod. Again, same lens, same camera, ISO 400. This was a couple of years ago when we had noctilucent clouds during the summer. This is a 4-second exposure because it was deep twilight rather than a dark sky. Excuse me. But again, that's enough to get things like the aurora. You can take pictures of meteors by doing 30-second exposures. You know, you can take pictures of constellations. This is a pretty basic setup, and you can even do a bit of stacking as well. So if you fancy taking a picture of like the star trails, what you can do is to take a series of pictures without moving your camera and then use software like Star Stacks, which is free, to just add all your images together and you get a nice picture of star trails like that. If you try to do the same picture, so that's 15 by 30 seconds, so what, 7.5 minutes? If you did a 7.5 minute exposure rather than 15 30-second ones, you would get the sky just blown out with light pollution. You would see virtually nothing, not even stars. But if you do shorter exposures and add them together, you can kind of counteract light pollution and things like that by reducing them in shorter exposures. So Star Stacks is a really nice free piece of software to do star trails with. The Milky Way can be captured without any tracking mount. Again, this is taken from Ingram a couple of years ago. This is Nikon D90, ISO 800, 18mm, 20 by 30 seconds stacked. Okay, I didn't use any calibration frames because I didn't think I needed to after I saw the result. So again, each individual exposure didn't look like that, but when you stack them together, it boosts the signal to noise and you can therefore bring out the Milky Way a lot more clearly. This one, I think I probably did a bit more manipulation in Photoshop because the foreground of that, I think I took from one of the images. If you stack everything together, the Milky Way moves, as do all the other stars. And the back, if you kind of you smear the background out if you stack on the stars. So I think I did a kind of a composite of two pictures here to get that one where the foreground was a little bit sharper. It's cheating, really, isn't it? It's not proper science. That's why it's not science. I don't know if Ian's here, but Ian sent me an email, and he's not the only person to ask this, but focusing can just destroy your evening if you can't do it properly. So you might think you're focused, and then at the end of the evening discover that you've got 3 hours of blurry pictures. I mean, it's happened to me before, but focusing a camera is a nightmare sometimes. I've discovered recently that my Nikon D90 focuses perfectly if I point it at Jupiter. and lock the focus after I've done it. So I auto-focus the DSLR on a bright star or planet. Jupiter works really well at the moment. And then lock it. You can, if you've got live view on a camera, you can try to do that. You can zoom in on the live view to maybe distant lights, so something maybe a kilometer away if possible, and then focus on that using live view. Or you can focus during the daytime on something distant and then make sure you don't change the focus between daytime and nighttime. That's a bit more risky, I guess. But focusing is a really tough issue. You can get tools to help you. I think you can get Bartonov masks for cameras as well. In red, don't forget to remove it, because at least a few people on the Facebook group have said that they've done this, where you put the mask on to help you focus and then forget to take it off. Again, what this does is it's a patterned mask which fits over the end of the camera or the telescope, and it makes it easier to focus, because what you're trying to do is to line up lines to get a perfectly symmetric star. And if you're out of focus, it's easier to see. Even if you're a little bit out of focus, you can see when those lines don't exactly cross in the center. So a Bartonov mask, it's not an expensive thing, and personally I don't use one because I've got a system that seems to work well enough now. I usually focus with if I'm taking pictures with a CCD camera, I will just focus on a double star before I image my main target. So I'll pick something like Albireo, where you've got like a fainter secondary component, and it seems easier to focus double stars than single stars sometimes, but that's how I do it. I use the DSLR to focus on Jupiter or a bright star, and a CCD camera, I'll find a double star before I start. Nope. Oh, I thought I was going to put a picture in there. So you can use your camera with the telescope, as I've mentioned. Now, finding the field of view depends on your telescope and your camera. So there are field of view calculators online where you can put in the details of both, and then you can type in the name of an object, and it will show you like how big the frame is compared to the object, and you can decide whether that's something you want to continue with. The way to get pictures of objects is to take lots and lots of them. We call them subs or sub-exposures. The number of subs that you need to get a good signal to noise ratio depends on like the brightness of the object. It depends on the surface brightness of it, the size of your telescope, your camera sensitivity. All of these factors will feed into the optimal number of sub-exposures that you need. Also things like how high the object is above the horizon, whether it's twilight or fully dark, whether it's moonlight or not. But typically when you're imaging deep sky objects, you're talking about spending like at minimum like half an hour. At most, well, there's no upper limit really. 2-3 hours will get you reasonable signal to noise ratio. But if you continue your session over multiple evenings, you can do dozens of hours if you have the patience for it. So it's not unusual to spend many hours. Personally, I can't fixate that long on a single object. I feel like we get so few clear nights that I have to photograph everything on a single night. So when we get to like 45 minutes of exposures, I'm really itchy to move to the next one, or I really can't feel like I'm hanging around on a single object. But in the end, I regret it because the images aren't as good. So I know I should try to do that this autumn. When it's a clear night, just pick one target and try to get pictures of that and get a really good picture. Some examples of pictures that I've taken with the Nikon. This is M15, which is in the constellation Pegasus. It's a globular cluster. So hundreds of thousands of stars there. I took this with the 8-inch telescope, my Need LX10, Nikon D90, ISO 800, and this was 45 minutes of exposure time with calibration frames. So 45 minutes because it was a fairly bright object, and I was happy with that. This is a galaxy in Andromeda, the other Andromeda galaxy. This is NGC 891. It's an edgeways-on spiral galaxy. And again, this is 44 exposures of 3 minutes each with calibration frames, ISO 800. So these are the kinds of pictures you can take with the DSLR. Now, obviously, I've mentioned this, but because you're kind of taking long exposures through a telescope, your telescope must be tracking fairly accurately during the exposure. So if you've got an equatorial mount and you polar align it, it either has to be done fantastically accurately, or you have to get into auto guiding, which means fixing another camera to maybe your finder scope or another little telescope. And that kind of corrects for any errors in the alignment of your mount if you weren't polar aligning exactly. So you have to do that to be able to take exposures of like more than probably a minute. This is a different telescope. This was the little 80mm refractor, Nastro's own little refractor, Nikon D90, ISO 800, 45 by 3 minutes with calibration frames. The Pleiades is one of the easiest objects to take a picture of, and it's quite big in the sky, so you need a fairly wide field of view to take this picture. And the tricky thing, I guess, about objects like the Pleiades is that the stars are so bright that they can overwhelm the nebulosity. So you might end up learning tricks about masking the stars in Photoshop so that you can enhance the nebulosity. But to be honest, your pictures of the Pleiades come out pretty well out of the camera. If you take like a 3 minute exposure, it looks pretty good anyway. This year I got a CCD camera. It was I ordered it in February before coronavirus was a thing, and it got delayed because of coronavirus, so I didn't receive it until I think it was early May. And then we had the summer where I couldn't really use it anywhere because the sky was too bright. So I've had very few opportunities to use mine, but it's a CMOS camera that I've got. Traditionally, you've got charge coupled device CCD cameras. CMOS are cheaper to manufacture, and therefore they're cheaper to buy, but they more or less do the same thing. CCDs are more preferred for serious science, but they can be fan cooled as well, which reduces the internal thermal noise of the camera. The one I've got, you can cool it down to like 25 degrees below zero, I think. So it can really reduce the noise in your images. So the other advantage is that they tend to have a higher dynamic range than a DSLR. That means you can capture like really faint stuff at the same time as capturing really bright stars. It won't kind of like blow the stars out so that you lose the nebulosity completely. So they're much preferred by astrophotographers to DSLRs. The few opportunities I have had to use it, this is a picture of the Eagle Nebula taken, I think, in May when I first got it. So I've got a Zoom ASI 533 MC Pro. It's a color camera, okay? So these cameras can be mono or color. Mine's a color. The temperature was set to -10 degrees Celsius. I also used something called a tri-band filter, which I'll tell you about in a minute. But it was a good way of reducing light pollution and letting through the colors of the nebula at the same time. And I applied calibration frames as well. In the center of that picture is the pillars of creation. The famous shot by Hubble is that middle bit. So this is an active site of star formation, and it was I was really happy to get that picture, but I've got very little from it since. Now, filters are used in astronomy to isolate particular colors of interest. So I'm going to talk about broadband and narrowband in a moment. Broadband, well, broad just means big in this context. So you've got all the colors of the spectrum. A broadband filter will let through lots of them. So it might be like all of the reds come through. and maybe some of the orange. A green will let through the green part of the spectrum, and the blue lets through the blue. But obviously there are more colors across the spectrum than just red, green or blue. You can combine those with mono cameras to make color images. Now the difference between color and mono is resolution in some ways, because in a color camera you've got a little array of sensors made from red, green and blue pixels, and in a mono camera you just have pixels which just are sensitive to light. So color cameras tend to have a lower resolution than a mono camera does. I think I'm right about that. So if you can, you should get a mono camera, and then you can have color images by using filters, and they'll be a higher resolution than the equivalent color camera would be able to produce. So I've got a color camera because I don't like messing around with all that stuff. I just want to get my color images fast, and I sacrifice a little bit of resolution to do that. Narrowband is where you allow very specific colors of light through to the sensor and you block everything else. I'll show you a picture to kind of clarify what I mean by this in a moment. So typical narrowband filters are oxygen 3, hydrogen alpha, sulfur 2, hydrogen beta, and there are others as well. And you would use those with mono cameras. Now I've mentioned I've got a tri-band filter, and a tri-band filter is basically a filter for a color camera that has all of these in the same filter. It allows these different wavelengths through in the same filter. There are other filters as well. So for example, if you've got a refractor and it's an achromatic, they suffer a little bit from kind of like color fringing around bright stars. An infrared ultraviolet cut filter will reduce that to some extent. As I found out this year, an ultraviolet filter is a great way to image details in the atmosphere of Venus. Okay, so a UV pass filter will block everything except for a specific range of ultraviolet light, and within that ultraviolet light are details in the atmosphere of Venus. So if you're only recording that, you're going to get some detail. I haven't got one, but a methane pass filter is great for the outer planets as well. It shows up the belts and zones on Jupiter. So yeah, so there are lots and lots of dedicated filters for kind of like taking the kind of picture that you want. A broadband filter does this. So this is meant to be the entire range of colors in the spectrum that you can see. So you can imagine a rainbow of colors here. A blue broadband filter lets through a lot of the colors that are associated with blue. The green blocks out the blue and the red and only lets the central part through, and the red blocks out the blue and the green, and you only let that through. I'll show you what that means in a minute, but if you had a mono camera, you would put a red filter over your camera, take some pictures, put the green filter over, take more pictures, put the red filter over, take more pictures, and then combine them to make a color image. Narrowband looks like this. So you can see it's letting through very specific colors. So hydrogen beta is a blue color, but it's a very specific shade of blue, and it blocks out everything else. So if you put these in front of your camera, because you're only letting through a fraction of the total light coming from the object, you're going to have to take a much longer exposure to get an image of the object in that color. So you do have to take longer exposures if you're using narrowband filters. Yeah, and the reason these wavelengths, these colors are chosen is because it tends to be interesting processes within nebulas. So it's usually like hydrogen fluorescing, emitting light of these particular colors. So if you can isolate these lights, you can kind of bring out the contrast in different features in the nebula. So oxygen 3, well, that's associated with ionized oxygen. So you get that in planetary nebulas. So planetary nebulas tend to shine very brightly in these colors as well. Now, Mark has very kindly supplied some narrowband images for me to kind of like show you. So we've got the hydrogen alpha image at the top, an oxygen 3 in the middle, and a sulfur 2 at the bottom. And you can see that through each filter, they look very different. This is aimed at the bubble nebula. So it looks different in each filter, and it's different physical processes emitting these different colors of light. So you combine them together to make a color image, and it looks like that. Okay. You can choose different palettes as well, so you don't have to put them, you could have the hydrogen alpha being red, you could have the oxygen 3 being green, you could have the sulfur 2 being blue, but you don't have to. There's different palettes that you can use as well. These are false color images. They're not a reflection of what you would see with the eye. And what would you see with the eye anyway? It wouldn't be anything like this. So the Hubble Space Telescope uses a particular palette as well, where you've got nice blues and yellows for different elements as well. So there are different palettes you can use to produce different colors, and they choose different palettes because it draws attention to the differences in the different wavelengths that were used more effectively than maybe red, green and blue would be. This is my new toy, which I got to play with for the first time last night. It wasn't really clear, but this is a hybrid. I like to call it a hybrid. It's not a telescope. It's a camera lens stuck on my ASI 533 with a Nikon adapter. And inside the adapter is a tri-band filter. The tri-band filter just lets through light of hydrogen alpha, oxygen 3, and hydrogen beta as well. So there's a filter in there as well. It wasn't a clear night. I don't know if anybody popped their head out the door last night to have a look at the sky, but you could see 1 or 2 stars, but it wasn't particularly clear. So I tried it. I just wanted to see if it would focus primarily. So I took a quick picture, and that was kind of, I'm hoping it sort of shows up there. That was a picture of the laptop. This is through cloud, and it's picked out the North American Nebula. This is Deneb. This is Cedar. This is the region of nebulosity around there. I can't wait to get a clear sky to see what this thing can do. But this is the camera lens is acting as a little telescope, and it's allowing me to take very wide field, narrow band images of the sky. And I'm really looking forward to see what this can do in the future. Okay, so that's kind of like how you do deep sky astronomy. You take lots and lots of long exposure images, you stack them together, hopefully with calibration frames, and then you can process the hell out of them after that in Photoshop. You can increase the contrast or do different things, but the hard work is getting the images. Pictures of the planets are different, okay? They have some similarities, but they're different because they're bright and they're tiny in the sky. The picture there is a picture of the telescope pointed at the crescent Venus a few months ago. And I'm having to track the planet with the 8-inch telescope. I've got a CCD camera, a fairly cheap CCD camera in the telescope. For this kind of imaging, because the planet is so bright, you have to take a very short exposure. And the atmosphere really disrupts things, makes it blurry, distorts the shape of the crescent in this case. And you find that it's not possible to take a single picture and for that picture to be very good. Maybe you'd have to take 1,000 for one of them to just happen to be in a moment where the atmosphere was calm. Okay, so that's suggesting that maybe we take lots and lots of images and we look for the best ones in amongst all the rubbish. So lucky imaging is the key to getting good pictures of the planets. You can do this, I guess you could do this in theory with DSLR, but I think when you capture video on a DSLR, it's probably going to have some kind of compression in it, which will actually throw away the differences between the images that you need. If you've ever uploaded an image to Facebook and seen kind of like blocky artifacts within your picture and thought, oh, I'm not happy with that, I suspect that's what your camera would do as well, to do a bit of compression on video. You need to be able to have a camera which can take uncompressed images in the form of a video or individual images. So what I'm going to tell you works for the planets and for taking close-up pictures of the moon. Again, apologies, this seems like I'm showing off, but these are a series of pictures of the planets which I've taken this year through various cameras. So Mercury was captured during daylight. Venus is I usually get it in daylight as well, before the sun goes down, while it's still high in the sky. Mars taken probably a few weeks ago, Jupiter taken a couple of weeks ago, and Saturn as well. So the technique I'm going to show you now will get you pictures like that if you can track the object. If you want to take pictures with the DSLR, they're actually pretty good for the longer exposures, which can capture the moons of the planets. So again, I've managed to get the bigger moons of the planets Saturn, Uranus and Neptune using longer exposures. So like 30 seconds through a telescope is enough to pick out the moons of the planet, but leave the planet overexposed itself. Right, I don't know how well this is coming through on your end, but that's a video of Mars taken with my ASI camera a couple of weeks ago. Hopefully you can see how rubbish it looks. There's kind of a hint of detail in it. There's a little dark mark there, but the distortion that you can see is caused by the atmosphere. So none of those individual images is very good. I mean, a movie is just a series of frames, individual frames. So I took something like 10,000 frames of Mars. I think it might have been 14,000 actually for this. And most of them are rubbish. But what you can do is to get a computer to look through all of those thousands of frames and select the best ones. Now, best, well, what does that mean? Best picture of a planet. Well, sharp, I guess. So you can train a computer to look for sharp images. Those are images where it goes suddenly from dark to bright, a sudden jump. If it goes smoothly up from dark to bright, that means it's blurry at the edge. So you get the computer software to look for edges that are sharp and then reject all the images that are not sharp. And it's a very few number that actually are. So the software that I used to use was called Registax, but I found out that a new one called AutoStackert does a better job for the selection, and it's faster, so I use that. In AutoStackert, what you do is you open your image, open your video file. It's quite simple to use, actually. It looks a bit intimidating because it doesn't look like a normal Windows program. It opens two dialog boxes, basically. But you open your video, you select whether you've got a planet or the surface of the moon. You decide whether you've got a noisy image or not and set that accordingly. So if it's a really noisy image, you bump it up to like the upper limit of 8. If it's a really good clear image, you put it down to maybe 2 or 3. You analyze, and then you choose alignment point. So if you can see any detail on the surface at all, you put an alignment point on there, or you can do it automatically. You can get the software to just have a guess at putting alignment points on. All this is going to do is to keep track of the distortion, I think, between the points that you've selected, and try to minimize them so that it's only stacking kind of, or choosing the best images, the ones that are not varying too much. I'm a bit hazy on the details of this, but I chose to stack 10% and throw away 90%. So that's a lot of rubbish. So most of the frames that you took get binned, and it's only the best ones that get kept. So after you've done stacking, remember, you're going from this. After you've stacked, you've got a nice smooth image, which you can now open in Registax. And Registax uses a system called wavelets, which is a way of bringing out the detail at different scales in the image. So you can move these sliders around over here, and it's just trial and error, just play around with it. So move it up. If it looks like it's too noisy, you can denoise it a little bit to make it look a little bit less grainy. Then when you've finished playing with it, you've got an image which looks a bit like that. So it's not brilliant. I mean, I took it when the atmosphere wasn't that steady, but it's a lot better than the individual frames were. So after you've got that, you can maybe contrast, stretch it a little bit more if you want, but usually that's the end point there. That's it, it's done. So just to kind of summarize the process, you take raw video, which doesn't look very good, you stack it, which improves things a lot, and then your final image, you play around with the wavelets, you enhance the detail in the surface until you've got an image that you're happy with. And you do that over and over. So look at that, 14,000 frames, and I used 700 in the end to get that picture stacked and processed. Now, you can do this with mono cameras as well. So the process I just described to you can be done with a mono camera with different filters in front of it. So I've done this with a picture of Mars as well. So with the red, green, and blue filter, well, just look at the differences between the images. In red and green, you can see these surface markings, but in blue, they kind of disappear. And you can see around the edge of the blue image, there's a kind of light boundary there. And that's actually cloud in the atmosphere of Mars. It's hazy cloud, which is more visible in blue than in the other colors. So you combine those again. This is your red channel, your green channel, your blue channel. You know, they're mono images, they're black and white, but you're telling the computer this represents the red component, this is the green component, this is the blue component. And in the same way that kind of like the elements on an old CRT would be brought together to make a color picture, you get your color image out at the end of it. One last thing to mention, if you've gotten that far with your planetary images, there'll be another problem that you might notice, and it's that the planets rotate. So Jupiter and Saturn spin very quickly, once every 10 hours, which means that if you're taking lots and lots of pictures of Jupiter, if you do more than 1 minute, you're going to see a kind of smearing out of the detail because Jupiter's rotating before your eyes. So how many images can you get in 1 minute? Well, with my camera, I can get about 3,000. With faster cameras, you could probably get 10,000 or more, okay? But if you continue to expose, the planet will smear out, and when you stack them, you'll get a blurrier image. So you have to try and keep your exposures down for Jupiter and Saturn. Mars is less problematic because it takes 24.5 hours to rotate. So you can do a few minutes with Mars. And Venus, well, it's the cloud tops which rotate around the planet, which you're imaging. So it's 2 to 3 days. So in principle, you can do like probably half an hour and you won't really notice anything change. So you need to bear that in mind. So if you're taking red, green, blue images of Jupiter, you might do 1 minute in each filter, and you might spend a bit of time changing the filter like I do, which means you spend 5 minutes imaging Jupiter, which means you can't stack the images without blurring at that point. So I had to learn how to use a new program, which was WinJupos. So you can use this to de-rotate your images. It's quite clever. What the program does is you put in the date and time of your observation, and you measure each image that you stacked. So you would stack all your images to get your red filter, then your green one, then your blue one. So you've done all your stacking and you've now got red, green and blue, but they're slightly different because Jupiter is rotated. And you tell the program the time that you took each image, and what it does is it transforms it to make it rotate slightly, and it matches it up to the same time for each image. By doing that, you can produce a color image which has been de-rotated and contains no blurring. And if you do that multiple times, so you do that, and then you do it again 20 minutes later, and then 20 minutes later, you get a series of images again, which you can then de-rotate, and it's like you're stacking these new planetary images on top. And you can do that up to a point, but you can really kind of, again, get top class images by doing that. I've not gone that far yet. I've just de-rotated my red, green, blue images. Finally, I guess all of this applies to taking close-ups of the moon as well. So you're taking lots and lots of images. The good thing about the moon is it's the shadow moving that would change the appearance of it. And the moon takes 27 and a bit days to go around the Earth, which means that the Terminator is moving very, very slowly across the moon. So you could take, I guess, 20 minutes of images, stack tens of thousands of them, and get a really good image of the moon. And again, stacking and wavelets will bring out the detail, as I did with the picture you can see there. Right, I've talked about a lot of software. Really, when you buy a camera, like a CCD camera, there'll be like software that comes with it that you either get on a disc or you download from the website. But there is free software as well, which can connect to your camera. So Fire Capture is a good one, and it's free. When it comes to stacking, Deep Sky Stacker is free. There are others. I've used Astro Pixel Processor, but it's commercial. It's you can buy a license for a year, or you can buy a lifetime license. It's about, I think it's about £60 for a year. PixInsight is very, very sophisticated. Steep learning curve, never used it. I gather it's quite expensive, but people who use it, they can talk to you about it. I think Mark probably uses it. He might be able to tell you a bit about that. Auto Stacker, it's good for stacking the moon and planets. I haven't really mentioned it, but I used Sequator for taking pictures of the comet with the landscape a couple of months ago when Neowise was in the sky. It's really good because you can take a picture of something like the Milky Way with the foreground, and then you kind of like bring all your images in to stack. And you can quite easily draw on your picture to show this bit is the landscape, use that in the final image as the landscape, and stack everything else as if it was a deep sky image. So Sequator is really good, and it's free. For post-processing, Registax is almost essential. I don't know of any other programs that do what it does. Photoshop costs money, but it's brilliant. GIMP is free. It's been a few years since I've used GIMP, but I imagine it would do a lot of the basic contrast stretching and enhancing. Beyond that, there are plugins for denoising images, for sharpening things, for removing background gradients, for boosting star colors, adding diffraction spikes. Lots and lots of things you can do to your image to make them look more how you think they should look. At the end of the day, when you take a picture of the Andromeda Galaxy, you're probably not going to be happy with it until it looks like somebody else's picture of the Andromeda Galaxy. And that makes it art, I think. Anyway, you might disagree with me on that, but we're not doing science at this point. Right, I think that was probably it. So I'm going to stop talking at that point.